These are the notes for Chapter 8, Day 78. We're going to spend 2 days on trig substitution, and what's going to happen is when you see square root statements, either a squared minus u squared plus u squared, or u squared minus a squared, it's going to be much more convenient to replace those square root statements with some sort of a trig statement. And the relationships you've seen before, if you see a squared minus u squared, then you're going to say that sine theta is u over a. Sine is opposite over hypotenuse, so that's going to help us get rid of this kind of messy statement inside an antiderivative. If you see a squared plus u squared underneath the square root, then you're going to replace tangent theta with u over a, which becomes u is a tangent theta. And finally, if you see u squared minus a squared underneath the square root, cosine theta is a over u, which means u equals a secant theta. Here are 3 antiderivatives that you saw earlier. You might want to refresh your memory with those 3. We're going to walk through 2 examples and show you how trig substitutions make antiderivatives a lot easier. So in the first example, we see square root of 4 plus x squared. That matches the pattern a squared plus u squared, in which case we have a is 2 and u is x. The triangle that we draw looks like this, and the substitution we're going to make is that x equals 2 tangent theta. When we take the derivative, we get dx equals 2 secant squared d theta, and now changing x and dx into these 2 statements produces this. Now that doesn't look like it's much better, but using some trig identities is going to simplify down quite nicely. Factor out a 4 from both of these terms, and then take the square root of that factored out 4, and you get 2 on the outside. 1 plus tangent squared is secant squared. The square root of secant squared is secant. And now on the top, secant squared divided by secant in the bottom produces the antiderivative of secant, which we know is the natural log of secant theta plus tangent theta. Now you're going to go back to the triangle that you drew here and change your secant and tangent thetas into x statements. Secant becomes hypotenuse over adjacent, square root of 4 plus x squared over 2, and tangent becomes opposite over adjacent, x over 2. This is your answer from this point on. It's just a couple of log properties. Add the 2 together to get this. Realize that you have a numerator and a denominator, so the numerator can stay put, and then minus the natural log of the denominator. Natural log of 2 is just a constant, so I'm going to combine these 2 constants together and get a new constant. Some books leave it as c, some books change it to a different letter, so I changed it into a d, and then the natural log statement with the variable stays. So that's pretty much the process. If you see square root statements, pick the appropriate substitution, use your trig identities, should make the antiderivative a lot more efficient. Second example, this one looks really quite ugly, but I'm going to take that 1 minus x squared, and to the 1/2 power becomes the square root, and now I can see which substitution to use. I've got a squared minus x squared, so I'm going to use sine theta is x over 1, which means x equals sine theta. Dx is cosine theta d theta. Plugging these 2 things back into the original statement produces cosine cubed over sine to the 6th cosine theta d theta. If I take the 4 cosines up top and match them with 4 match them with 4 sines in the bottom, I have 4 cotangents with 2 sines in the bottom left over. That's 2 cosecants. Using a u substitution where u is cotangent theta, du is negative cosecant squared theta d theta. That's take care of all this as long as I throw in an extra subtraction or negative sign, and then I've got u to the 4th power. Notice that the limits of your integration change. Don't forget, the original statement was in terms of x, so 1/2 and 1 are the bounds or the limits of your antiderivative. As soon as I change things to thetas or u's, those limits change. So the antiderivative u to the 4th is 1/5 u to the 5th. Change my u back into cotangent theta, and then I'm going to change cotangent theta back into x's. So I look up here and say that cotangent theta is square root of 1 minus x squared over x. It's adjacent over opposite. Now I can finally, since I'm in terms of x's, substitute in my values 1 and 1/2. Substituting those in, I get this statement. A little bit of simplifying produces 9 root 3 over 5. So that's the process. I would highly encourage you to draw triangles because that helps you navigate, especially the resubstitution back and changing things back into your x statements.